Yeah, and let me share screen. Okay. Do you guys hear me who are in the Zoom? Do you guys in the Zoom hear me? Yeah. Okay, great. Thank you. So, yeah, great. Thanks. So, hi, everyone. Before we start the session, let me tell you that my father is here. Yeah, and my father, Yusuf, and he has come from Iran to see me, visit me, and he's my guest for 2 weeks almost. Okay, and yeah, thank you, and I'm happy to have him here. Okay, so we're gonna continue where we had left off, but before that, let us review a bit what we had for support vector machines. Okay, so what did we say? Yeah, we said that SVM. So at that time, long time ago, about 1958, people were thinking about, okay, how to have classification for binary classification. And then we said, okay, they said, let's find some decision boundary, assuming that they are linearly separable. Let's find a decision boundary which partitions the space into two parts where we don't have any misclassification, and depending on the random initialization that we choose, we might end up with different decision boundaries. Then someone named Vapnik and his team came up and said, okay, let's find the best of them. Which one is the best decision boundary? Then they said, okay, so the best decision boundary is the one which has the largest distance from the closest points of the two classes to each other. And it means that it's exactly in the middle of two classes. And how do we find that? Of course, it's optimization, right? We should find it. Of course, how do we find that? Of course, this is an optimization problem. We need to model it as an optimization problem, because machine learning is all optimization plus some other stuff such as probability and linear algebra and these things. Okay, so first off, they said let's have hard margin SVM. This was the first idea that they had. They assumed that the classes are completely separable, linearly separable. So they want to find some decision boundary. In 2D it's a line, in 3D it's a plane, so in multiple dimensions is a hyperplane, right? And this equation one is just a you can see that the equation of a line, the decision boundary, right? So we worked it out last session, and we modeled the distance of a point from the decision boundary, and then for the distance to be positive, we use a trick here as done in equation 4 and 5. So to make it, to get rid of the absolute value, which is non-smooth, and then this is a good technique in machine learning. So in this way, the distance will be positive, non-negative, I can say. And then we maximize the distance as was the goal of SVM. Then we said that, okay, so let's maximize this, and then we improve the modeling of the optimization problem, and then we form the Lagrangian. First, the inequality constraint, we made it a standard form, and then we wrote the Lagrangian, and then, as done in the method of Lagrange multipliers, we took the derivative of Lagrangian with respect to the optimization variables, primal optimization variables. We set it to 0. We set them to 0. We ended up with two equations, important equations in SVM, equation 12 and equation 13. Okay. And then what did we say? We said, okay, let's put the what we found for the primal variables, but taking the derivative of Lagrangian with respect to primal variables and setting that to 0, we found some equations. Let's put them back to the Lagrangian. This is what we do in method of Lagrange multipliers. Okay, for more information on that, see my optimization course. So we do that, and the Lagrangian then will be purely based on only dual variables. Okay, then in this way, so we did that. That will be when we do that, when the Lagrangian will be purely based on the dual variables, that's called the dual function G. G here, as done in equation 14, you can see we only have alphas here. And x's note that x's are the input data. They are not primal optimization variables. So we also have some conditions on the dual variables for inequality constraints, as shown in equation 15. We did that, and then we formed the dual optimization problem, which is equation 16, in method of Lagrange multipliers. When we have the primal optimization problem is minimization, the dual optimization problem becomes maximization, because there are, like, as I showed here in this figure, there are like two balls back to back. The gap might be 0 or might be positive, but the gap is never negative. And then, so we moved from primal optimization problem, and we made it dual optimization problem, and we solved this dual optimization problem. This is a quadratic programming problem. It can be solved using interior point method or any optimization toolbox. It's an iterative. It has an iterative solution. Okay, but although it's iterative optimization, it always ends up to the same solution. Okay, why? Because this is a concave optimization problem. It has only one global solution. That's why it doesn't matter where because in iterative optimization, we also start with random initializations, right? But no matter where you start, you will end up with the same solution for this, for SVM. Perceptron was not like that. Okay, and then we have some KKT conditions. Based on this, we analyzed why we have some support vectors. And we talked about where the dual variables are 0. But we said that we analyzed that for support vectors, the dual variables might be non-zero, might be 0. Usually they are non-zero, but for non-support vectors, they're all 0. We talked about that. And then, yeah, this is our analysis. Then we said, well, we also talked about the test phase of the SVM. Then we went to the soft margins. So this is an improvement of the SVM. They said, what if we have some data which are confused from the two classes? So they are not completely linearly separable, but they are not very hard, very nonlinear. If they are very nonlinear, you can't, for example, if they are like this, there are two rings inside each other. So this is one class, this is the other class, and this is completely nonlinear. You can't do, you can't use even soft margin SVM for this. Okay, but what soft margin SVM want to do is something like this. So they are almost linearly separable, but you might have something like this too. So as you see here, you can't draw any line which completely purely separates them, but so they are not linearly separable, but you can tolerate these small misclassifications, right? Something like that. So these ones. And then so they said, let's tolerate that. And by toleration, we mean penalty in mathematics and optimization, and penalty means regularization, right? So let's regularize the optimization problem. As done in equation 24, we introduced several zeta variables, which are the primal variables, additional primal variables, and then we solved them. And again, similar to before, we formed the dual optimization problem, formed the Lagrangian dual optimization problem, and then we said that we can solve it using it's again a quadratic programming problem. And then here we said that it's a quadratic programming problem again. We can solve it using any optimization toolbox, which may use interior points method or other algorithms for this quadratic programming. So it can be solved easily. And then again, using the KKT condition, K-Roche-Cohn-Tucker conditions, we analyzed them. We analyzed the support vectors and non-support vectors. This is what we did in last session. Now, this is where we left off the last session. Okay, now we want to talk about kernelization in machine learning, which is using kernel SVM. So it was almost at the end of the 20th century, okay, where Vapnik and his team, they said, what if the classes are completely nonlinear, like this, okay, like this, and we can't use the even soft margin SVM for it. So they wanted to propose something or a variation of SVM to be able to handle it. And why? Because at that time, Vapnik's group was working on the SVM and these things, and another team and maybe several other teams were working on neural networks. They were in competition. Neural networks were good for what? Handling nonlinearity, because of nonlinear activation functions in the middle of layers of neural network, we can easily handle nonlinearity. So Vapnik et al. Didn't want to do this competition. They said, okay, let's find a variation of SVM. So the idea of kernel SVM is that soon we have these two classes. Let's increase the dimensionality. Usually increase. Let's increase the dimensionality. So, for example, in this case, these are 2D, nonlinearly separable. If I increase the dimensionality and somehow I make it in a way that one of the classes comes up and the other class is down, then they become linearly separable. Using a hyperplane, linear hyperplane, I can simply separate them. So the idea is, let's do some transformation and then use the linear SVM. Okay. Now, before talking about kernel SVM, let me tell you about kernelization in machine learning. Okay. So linear algorithms cannot properly handle nonlinear patterns. So linear algorithms, such as SVM, they can't handle nonlinear patterns of data, obviously. When dealing with nonlinear data, if the algorithm is linear, or two solutions exist. So without even looking at it, you tell me, assume my data set is nonlinear. What can we do in machine learning to handle nonlinear? For example, I have a nonlinear classification problem. What can I do? The simplest thing, I think you will laugh, is that, okay, design a nonlinear algorithm. Okay, this is the simplest thing. Another thing is that, what if I want to stick to the linear algorithm? Yes, try to kind of transform data in a way that they hopefully they become linearly separable, and then apply the linear algorithm. Okay, so these are the two approaches that you need to do for handling nonlinear patterns of data. Okay, so as I said, either you use a nonlinear algorithm, or nonlinear data should be modified in a way to become more linear in pattern, and then we apply our linear algorithms. Some examples of this. So some examples of the first idea, which let's design a nonlinear algorithm from scratch. These are some examples: locally linear embedding and isomap. They were very interesting algorithms proposed in year 2000. Okay, they shook the world of machine learning, and we will go over those two later in this course. And some other examples for the second category, where we have nonlinear data. Let's transform them. Hopefully, they become linear, and then apply the linear algorithm. That's PCA, principal component analysis, but kernel PCA. So kernel versions of them: kernel PCA, kernel feature discriminant analysis, kernel FDA, and kernel support vector machine, kernel SVM. Okay, these belong to the second category. Okay, the second approach is called kernelization in machine learning, which we define the following. Note that kernel and kernelization are used a lot in different fields of science, and you shouldn't confuse them. We have kernel in linear algebra, which is something else. Okay, we have kernel even in operating system. We have kernel in various fields. You shouldn't confuse them. I'm talking about kernelization in machine learning. Okay, so this figure shows how kernelization for transforming data can help separate classes. As I said, we apply some transformation and they become linearly separable. By the way, in kernelization, so when we have some data set, it's called input space. It is in the input space. Why? Because this is a space of input data. Okay, this is called inputs. But when we apply some transformation to bring it for the kernelization, to bring it to some feature space, that's called feature space. So we bring in kernelization, we have some data in the input space, which is the original space of data. Then we apply some transformation. We bring it to another space, and we name that space feature space. Okay, feature space. And this feature space is also called RKHS, short for reproducing kernel Hilbert space. Reproducing kernel Hilbert space. Okay, RKHS. So generally there exist two main approaches for kernelization in machine learning. These two approaches are related in theory, but have two ways of kernelization. Okay, these are these. So there are two ways. One of them is kernel trick, the most well-known one. Kernel trick. For example, it is used in kernel SVM. We're going to use that. Okay. Another technique is kernelization by representation theory. For example, it is used in kernel FDA. We are not going to talk about kernelization by representation theory in this session, but later in this course, when we cover FDA and kernel FDA, we'll see that. Okay. But the first type we'll see today, which is in kernel trick, used in, or for example, kernel SVM. Okay. And here we explain the kernel trick using kernel SVM. By the way, I have a tutorial paper on kernelization in machine learning. I think I have referenced that in this slide deck. It's huge, and you can see it goes in depth of even the mathematics of kernels. So I'm not going to cover that because it will be overwhelming. But for interested students, you can take a look at that tutorial paper. That's also has appeared as a chapter of the book, Elements of Dimensional Reduction and Manifold Learning. It's summarized in that book, but its full version is in that tutorial paper. So for those of you who want to know kernelization from pure mathematics and those things, okay? Okay, kernel tree. So definition, feature map or pooling function. We define the map in this. This is the mapping. What do I mean by X? Fancy X. This is the space of data, or called input space. Okay, this is input space. What is this H? Fancy H stands usually for Hilbert. Okay, so this is a Hilbert space, or feature space, or RKHS. You're reproducing kernel Hilbert space. Okay, so I'm applying some transformation to data. And what is it? To transform data from the input space to the feature space, or Hilbert space, or RKHS. Okay, in other words, this mapping pulls data. By the way, RKHS is a special case of Hilbert space. We have various Hilbert spaces. One of them, which we use in kernelization, is RKHS. Okay, I have explained more in that tutorial. In other words, this mapping pulls data to the feature space. So this is a map where we have X. It is mapped to phi of X. Okay, this function phi of X is called the feature map or pooling function. So feature map or pooling function. Okay, why is it pooling function? Because it's like it is pulling data from input space to the feature space. Okay, so the feature map is a possibly infinite dimensional. Why? Because Hilbert space usually has larger dimensionality. Okay, that's why. Possibly it might be finite or infinite dimensional vector whose elements are this. So you can see phi 1, phi 2, by phi 1, phi 2. I mean, these are the elements of the vector phi. Okay. Let T denote the dimensionality of phi of X, where T might be infinite, right? The feature map may be infinite or infinite dimensional. That is, T can be infinity. It is usually a very large number. The Hilbert space may have infinite number of dimensions. I talked about that already. Okay. one technique to kernelize an algorithm is kernel trick. So I'm going to talk about kernel trick in this slide. In this technique, we first try to formulate the algorithm formulas or optimization in a way that data always appears as an inner product of data instances and not a data instance alone. What do I mean? So assume my data, my input data, not necessarily my optimization variable, my input data, okay, which is X, right? I formulate it in a way that in my optimization problem or in my formulation, I have some X transpose X, okay? I shouldn't have X alone. Otherwise, I can't use kernel trick, okay? So I need to have X transpose X or X transpose X. By capital X, I mean the matrix of the whole data. Vector X is small x is the vector of X, or X transpose capital X, or X transpose X. They should be all in the format of inner product. I have written them here too, okay? Not lonely X or X. In this way, kernel trick replaces X transpose X with phi X transpose phi of X. So whatever we see in the formulation X transpose X, we change it to phi of X transpose phi of X, okay? And this phi of X transpose phi of X, we call it K X and X, which is the kernel. K stands for kernel, okay? So K is a kernel function where is defined to be phi of X transpose phi of X, where phi is a pooling function, okay? And what does it mean? So what's the interpretation of this? Assume I have some X. When I say I always in my formulation, I have always X transpose X, what does it mean? It means that my formulation, my problem, doesn't care about X's alone, the data points alone. It cares about their similarity. When we say X transpose X, what does it mean? How X is similar to X. When we say X1 transpose X2, X1 is a vector, X2 is another vector. When you say X1 transpose X2, it means that inner product is a measure of similarity, right? It's a scaled cosine, right? So it means how similar they are, the two vectors. When I only in my formulation have X transpose X, it means that my algorithm doesn't care about X, the data points, where they are. It doesn't care about their exact locations. It cares how similar they are. The data points are with respect to each other. Then kernel trick says, okay, so your formulation is saying how similar they are in the input space. Let me see how similar they are in the feature space. This is the idea of kernel trick. So let's replace their similarity in the input space with their replace in the feature space. Okay, so as you see, we usually don't have phi alone. We usually don't have the phi alone. Why? Because what does phi do? So we have a bunch of data points in the input space. Phi of X transfers them to the feature space. What does kernel trick say? I don't care about the points alone. I only care about their similarities. So also I'm replacing X transpose X, which is the similarity of X's, with phi X transpose phi X, which means with their similarity in the feature space. So only similarity is important. Therefore, whatever is important in the feature space for me is phi X transpose phi X, not phi X alone. Similar to the way that in the feature space we say our formulation doesn't care where X is, our kernel trick also doesn't care where phi of X is. It only cares where what is the similarity in the feature space. That's why usually in the kernelization, we don't have phi of X alone. We have phi of X transpose phi of X. And as this is very important, this term phi of X transpose phi of X, we name it. We define some function named kernel function, and we denote it by K of X and X. Okay. So because kernel can be computed by inner product between the pooled data instances. This is the definition of kernel. Okay. See our tutorial for more information. Therefore, the inner products of points are all replaced with the kernel between points. The matrix form, so this was the vector form, right? Now, what if we have the whole data transpose the whole data points, okay? Assume, what is this X? It has the data points as column vectors in its columns. It's a matrix, right? So X transpose X means that the similarity of all points with respect to other points, okay? So you can replace it with phi, and then here phi of X is also a matrix, right? Phi of X transpose phi of X, which is a kernel of X and X. Here, kernel was a scalar. Here, kernel becomes a matrix. We call this kernel matrix, okay? Most often, kernel matrix is computed over one data set, like this, like equation 43. Then in this case, it becomes a square matrix, right? N by N. So hence, its dimensionality is N by N. However, in some cases, the kernel matrix is computed between two sets of data instances with sample sizes N1 and N2. Assume we have two data sets, N1, one of them has N1 data points and the other one has N2 data points. Then, as mentioned here, then by kernel trick, so between every, for the similarity or the kernel, we can have the kernel or similarity between every point of every pair of points from data set 1 and data set 2. This is a scalar, but we can have the kernel between the whole data set 1 and the whole data set 2. This becomes, yes, and this is a matrix of N1 rows and N2 columns, right? So it will not be a square matrix necessarily this time. Okay. And I think it's obvious now. Kernel is a measure of similarity. Okay. Okay. Now let's talk about well-known kernel functions in machine learning. So one of them is linear kernel. Linear kernel. Linear kernel is the simplest kernel, which is the inner product of points. What does it mean? In linear kernel, phi of X is X. So phi of X is the identity map. It doesn't do anything. So the feature space is the same as input space. You might be wondering, what's its use? It has uses, I will tell you. So as I told you, we have two types of kernelization, okay? One of them was kernel trick, the other one was representation theory. In kernel trick, it doesn't do anything, okay? When you use linear kernel, it's like you are not applying any kernel because X transpose X is replaced by X transpose X. But when you use representation theory, it makes a difference because of its formulation. Because in representation theory, you don't use X transpose X anymore. You do something else, which we'll cover later, okay? That's why linear kernel has its use cases, but it depends on your algorithm, whether you have kernelized it by kernel trick or something else by representation theory. If it is by kernel trick, it doesn't make any use, okay? So it's X transpose Y, as I told you. Comparing this equation with equation 44, which is this, okay, shows that in linear kernel we have this phi of X equals X. Hence, in this kernel, the feature map is explicitly known. Okay, another thing, I told you in most of the kernels we don't know phi alone, but in linear kernel we know it's X. Phi of X is X. Okay, so note that phi of X equals X shows that the data are not pulled to any other space in linear kernel, but in the input space. Okay, the inner products of points are calculated to obtain the feature space, right? Now, if you use kernel trick, the kernelized algorithm with a linear kernel is equivalent. This is important. Kernelized algorithm with if using kernel tree, kernelized algorithm with a linear kernel is equivalent to the non-kernelized algorithm. It means that, what does it mean? In kernel SVM, which uses kernel tree, if you use linear kernel, this is equivalent to SVM, okay? This is because in linear kernel, we have this, I told you already. Therefore, linear kernel does not have any effect when using kernel tricks such as kernel PCA, kernel SVM, and these things. Okay. However, linear kernel, I told you, if we use representation theory, it makes a difference. Examples are kernel FTA and kernel supervised PCA. Okay, they use representation theory. Now the other one, this is the most well-known kernel function. Okay, this is radial basis function, RBF kernel. or Gaussian kernel. Okay. RBF kernel has a scaled Gaussian or normal distribution, where the normalization factor of distribution is usually ignored. So what do I mean? Do you remember the formulation of this? Is exactly what we have, this exponential in the Gaussian distribution, but usually before that there is 1 over something, some scale, right? Why do they have that scale in the Gaussian distribution? Because they wanted to integrate to 1, okay, or sum to 1, integrate to 1. If you ignore that, it doesn't necessarily ignore sum to 1, but that you don't care, because you want to just have the behavior of Gaussian distribution. Okay, so they use RBF kernel in this way. And what is that? This is a parameter. You can see it as what? Related to variance, because we have variance here. Gamma is 1 over variance. Okay, and what is this? X minus y. So it means that the difference between x and y. Okay, if you see Gaussian distribution, you have x minus mu, for example. It means that the difference of x and the mean of distribution. But here we have 2 points, x minus y. Okay, so gamma is 1 over sigma squared, where sigma squared is the variance of the kernel. A proper value for this parameter is what? Gamma equals 1 over d, where d is the dimensionality of data. As far as I remember, how do I say that? I think Scalearn library, as far as I remember, says that. I got this line from the Scalearn library. Okay. Okay. Note that RBF kernel has also been widely used in RBF networks. If you have seen my deep learning course, I have talked about RBF neural networks, and kernel density estimation. They are used a lot in kernel. What is kernel density estimation? Just briefly telling you. Do you know histogram, right? A histogram of something. Now, limit the bins of the histograms to be as small as possible. So you limit the width of the bins to be small, limit to 0. It becomes a smooth histogram, right? A smooth. And this smooth histogram is kind of a distribution of data. It kind of estimates the probability density function of the data. That's called kernel density estimation. Okay. So there are several ways to fit a distribution to data. One of them is kernel density estimation. The other one is fitting a mixture distribution to data. We are gonna cover fitting a mixture distribution to data in this course. Okay. So another kernel function is Laplacian kernel. And what does it do? The Laplacian kernel, also called the Laplace kernel, is similar to RBF kernel, but with L1 norm rather than L2 norm, rather than a squared L2 norm. So see here, I have L1 norm, but here I have a squared L2 norm. Okay. And I think you know why people usually use L1 norm, sparsity and distance, right? L1 norm usually rings the idea of sparsity in our minds. Okay. Where this is also called, this L1 norm distance is also called Manhattan distance. Why is it called Manhattan distance? Because when we have 2 points, you go from here to here for L1 norm. This length plus this length is the L1 norm between them. This length is L2 norm. Okay. And what does it mean? So this is in 2D. In 3D, you will have 3 lines. So it's like, assume these are 2 points in the Manhattan city. Okay. And then L1 norm is like you go in the streets of the Manhattan city. But you can't, in L2 norm, you need to pass through the buildings. You can't do that in the city. That's why it's called Manhattan distance, because it's like you're moving on the streets of the Manhattan. Okay, so a proper value for this parameter is, again, gamma is 1 over d, where d is the dimensionality of data. By the way, some funny thing. I had an exam in several years ago. I had an exam in University of Waterloo about machine learning. I made a mistake about Manhattan distance. I forgot whether it is L1 norm or L2 norm. At the end I wrote it as L2 norm, and it wasn't. I remember I lost grade on that. After that, I found out the reason why it is called Manhattan distance. Okay, okay. So these are dimensionality of data. In some specific fields of science, Laplacian kernel has been found to be performed better than Gaussian kernel. You can see reference 22. This makes sense because of betting on a sparsity principle and also Occam's razor and all of them. We already have talked about it several times in this course. Note that L2 norm in RBF kernel is also more sensitive to noise. Why? Because it has a square. Whenever you have a square, you should be scared of outliers because you magnify the outliers. Okay, so that's why one of the drawbacks of L2 norm is magnifying the outliers. Although L2 norm is easier to work with than L1 norm. Okay, another one is sigmoid kernel. What does it do? Sigmoid kernel is a hyperbolic tangent function applied on inner product of points. So hyperbolic tangent applied on the inner product of points. X transpose Y. You have some variables, parameters, gamma and C2. Your gamma is the slope and C is the intercept. Some proper values for these parameters are gamma equals 1 over D and C equals 1. I think these are values are proposed by a scalar library. Okay, where D is the dimensionality of data. Okay, the other one is polynomial kernel. Polynomial kernel, what does it do? It applies a polynomial function with degree delta. Delta is a positive integer on inner product of points. So, right, if you set D to 1, it becomes a linear, right? Then D to 2, set D to 2, it becomes quadratic. 3 cubed, right? Cubic. So gamma again is the slope and C is the intercept. Again, these are the proper values. Okay, polynomial kernel. Polynomial kernel is used also a lot. RBF kernel is also used a lot. Cosine kernel is also an important kernel, although less well known than RBF kernel. So what does it do? It's a measure of similarity. We know kernel is a measure of similarity, as we talked about it, and computes the inner product between the points in the feature space. Cosine kernel computes the similarity between points. We know that X transpose Y is a scaled cosine, as shown in this equation. Cosine of X and Y is X transpose Y over L2 norm of X, L2 norm of Y. If X and Y are normalized, then inner product becomes cosine, equal to cosine. So this is cosine, the kernel. The normalization in the denominator projects the points onto a unit hypersphere. That's important. What does it do? So if you apply linear kernel or simple inner product, X transpose Y, it doesn't care about their lengths. It just computes. But cosine first brings them. If it is too long, it shrinks it. If it is too small, it expands it. So they both become on the surface of a hypersphere unit with unit radius. And then it applies the inner product. Okay. So note that angle-based measures such as cosine are found to work better for face recognition compared to Euclidean distances. I have this from my master's supervisor. She told me that. And I think, yeah, you can take a look at reference 25. So angle-based measures are working very well for face recognition. Chi-squared kernel. Assume xj denotes the jth dimension of the d-dimensional point x. So xj is the jth dimension of x. Then the chi-squared kernel, shown by this notation also, is this. It's defined as this. This is used. This is not well-known kernel, but it can be used. So it's one of the kernels. Its summation, what? Yeah, I think that's why people usually don't use that. So for this to be recorded, he said that it might be computationally expensive. I agree. That's why people don't use that much. But this is chi-squared, and gamma is a parameter also. Proper value is gamma equals 1. Note that the summation term inside exponential without the minus is the chi-squared distance, which is we have a distance named chi-squared distance, which is related to the chi-squared test in the statistics. So these are all related to each other: chi-squared distance, chi-squared test, and chi-squared kernel. Okay. So now that we have talked about kernel and well-known kernels in machine learning, by the way, there is also a scale-learn page for kernel functions. You can take a look at that. Sklearn has a lot of implemented all of these kernels. You can use them easily, okay, in code, in Python. Now let's talk about kernel SVM. What does it do? The kernel SVM was proposed by Vladimir Vapnik et al. In years 1992 to 1995, and that's that's the years where they were in the competition with neural networks. I told you that session. I'll tell you this time too. Vapnik was very good in mathematics. Why? How can we find out? Kernel was not an easy concept. Kernel was in functional, and first it was in functional analysis of mathematics, one of the hardest parts of mathematics. David Hilbert worked on that. Then it was around it was the end of 19th century at the start of 20th century. Einstein was alive at that time, okay? Then Hilbert was also, I think, alive. They worked on that. They developed kernels. That's why we call it reproducing kernel Hilbert space. Hilbert worked on that. Also Banach was Banach spaces. It's in functional analysis for those of you who like mathematics. So, and then after a while, people in physics found it useful. So they brought kernels to quantum mechanics. Then they used that in eigenfunctions that were developed for quantum mechanics, eigenfunctions. And then later, Vapnik, at the end of the last century, as you see, after almost 100 years, it entered machine learning. Okay, it entered machine learning. So what did they say? Recall equation 16. This was equation 16. Do you remember? In hard margin, this is the dual optimization problem for hard margin SVM. Okay. Then for kernelization, using kernel trick, we can replace xi transpose xj with phi xi transpose phi xj. And this is kernel of xi and xj. Why can we do that? As you see, interestingly, the dual optimization problem only has xi transpose xj in it. It doesn't have a single xi or a single xj. Okay, interestingly, so it can be we can apply kernel trick on that. Therefore, I replace this phi xi transpose xj by phi xi transpose phi xj, which is equal to kernel of xi and xj. Here it is. So this is an optimization problem. Okay, and note that it is possible to, by the way, take a look at equation 53. This is the dual optimization problem in kernel SVM. Do you agree that this is a quadratic programming problem as before? The only difference is that xi transpose xj is replaced by kernel of xi and xj. Do we have kernel of xi and xj? Because in hard margin SVM, we could easily calculate xi transpose xj, right? We have the points to calculate the inner product. Can we easily calculate the kernel here in equation 53? Yes. In a few slides ago, I showed you some of the formulations for the well-known kernel functions. Assume you use cosine kernel. What do I do? I replace this kernel by the cosine kernel. If you use linear kernel, it becomes similar to hard margin SVM. You use RBF kernel. Whatever you put here, you can easily calculate the kernel, right? So it's not hard to calculate. By the way, usually we don't calculate the kernel function every time inside the summation. We usually calculate the whole kernel matrix once, and then we read the elements of the kernel matrix. So what is k, xi, and xj? It's the ijth element of the kernel matrix of X transpose. So apply kernel function on the whole data set with respect to itself. So X transpose X becomes phi X transpose phi X. It becomes an n by n matrix. Then you have the kernels of all of the pairs. So for this k of xi and xj, you just take the ijth element of this kernel matrix. Okay. Now, easily solved. It is easily solvable by any optimization toolbox. So easy. This is kernel SVM. And it works very well. Note that it is possible to use kernel trick in soft margin SVM too. We did it for hard marginal stream. Soft marginal stream also has xi transpose xj. But why do we why don't we usually do that? Because what was the purpose of soft marginal stream? If we have some misclassifications, let's tolerate them. What is the purpose of kernel stream? If they are very non-linearly separable, let's handle them. We don't need to use any toleration anymore, right? Because we can easily increase the dimensionality by kernel and they become linear. Hopefully they become linearly separable. Although it is possible to apply kernel SVM on soft marginal stream. All right. Okay. Analysis of KKT conditions of kernel trick is the same as what we did for hard marginal stream. Okay. Now let's talk about kernel SVM versus neural networks. Because of usage of the kernel function, kernel SVM can handle non-linearly separable classes, right? It can handle it. And kernel SVM was winning the competition with neural networks in 1990, right? Because it was developed in that time. And the start of the 21st century. You can see it's not very far away from us. This time period is referred to as the winter of neural networks. So because Vapnik et al. Proposed kernel SVM, it caused a winter for neural networks. They were losing the competition. So the reasons of this overcome of kernel SVM over neural networks was this. First, kernel SVM was mathematically sound and solid. Whenever you propose something and it is mathematically sound and solid, you are very sure about it, and people usually respect you because of that algorithm. Okay. Kernel SVM was able to perform nonlinear classification. Okay, it was nonlinear. At that time, multi-layer perceptron neural networks could not, or deep neural networks, multi-layer perceptron could not become deep. Why? Because of two problems: vanishing gradients and exploding gradients. So gradient vanishing or gradient explosion. Why? Why does this happen in neural networks when you increase the number of layers? Because you have multiplication of gradients in the chain rule. Okay, backpropagation is what? Is gradient descent and chain rule. I have talked about it in my deep learning course. So you have multiplication of gradients. Assume the gradients are small. If you multiply too many small values by each other, they become very small, and in computer they become zero. Vanishing gradients. But if they are too big, if you multiply two big values by each other, then they will explode, they will overflow in your computer. Gradient explosion. So that was a problem. They couldn't make it deep, having a lot of layers. Okay. But there is a but. Since about 2006, neural networks came back and they finally won the competition over the kernel SVM. How? Neural networks could win the battle back against kernel SVM. The reasons are this. Kernel SVM, so these are the drawbacks of kernel SVM, are also what is good about neural networks. Kernel SVM required choice of kernel function. One of the things in philosophy is that when you have freedom, it gives you responsibility. Okay. Here also, we give freedom to the user to choose the kernel function, but it gives the responsibility to the user, which the user will say, which kernel function should I use? In the best case, the user might say, okay, let me do cross-validation and see which kernel is good for me. I don't know. Again, that's a philosophical problem. When you have freedom, it brings responsibility. Okay, so that's a problem with kernel SVM. But neural network does it all itself. Doesn't have any choice of kernel. So it was not obvious which kernel function is best for a data set. Usually RBF kernel was used by default. Calculation of kernel another issue of kernel SVM. Calculation of kernel function is time consuming. Why? Why? Usually it is symmetric, right? But still, although it is symmetric, its time complexity, I think, becomes O(n)², right? or yes, ON squared, if n is a number of data points. So it's ON squared is large. If you have big data and n is large, it's too hard to compute kernel function. Okay, so that thus cannot handle big data with huge n. This is why neural networks could handle big data. Neural networks were developed for big data. Okay. At that time, the world was facing the explosion of data at that time. Nowadays also. And information, explosion of information. And handling big data was crucial. Okay. Another problem, the problems of gradient vanishing and explosion, which I talked about here, were resolved using various techniques such as initialization by restricted Boltzmann machines or RBM. It was proposed by Hinton in 2006. Also, ReLU activation function in 2011 and dropouts technique in 2014. One of them is proposed by Hinton's group. One of them was proposed by Bengio's group. Okay, so they resolved the issue of gradient vanishing and explosion. So finally, kernel SVM lost the battle, but still it's respectful because of its theory and mathematics. Okay, and also it's usually fast, especially if your data is not big. So if you want to do something very fast, you don't want to do it with neural networks. Let's do it with SVM. Okay, more notes. For multi-class classification, we can consider every pair of classes as a binary classification. Assume so far whatever we talked about was binary classification. What if we have multi-class classification? Then we can consider every pair of classes, and every pair of classes becomes a binary classification problem. Okay. Therefore, a multi-class classification can be considered as a set of binary classification problems. Right. Okay. SVM can also be used for regression. What did we talk about? We talked about SVM and kernel SVM for classification. But we have SVM and kernel SVM for regression too. Okay, so that's called support vector regression, SVR. Okay, you can see paper 31. And clustering, one class SVM, paper 32. So it can be used for clustering too. It's called one class SVM. Okay. Here we went through SVM and kernel SVM for binary classification. But for SVR, it's like this. If you take a look at paper 31, you'll see that. It's like this. Its figure is shown here. Left figure, take a look at that. So what does it say? Its formulation, its optimization problem is similar to SVM. Hence, its name is SVR. And it says that, let me find some line which fits the data the best. Okay, here. By the way, linear SVR is linear, so it fits a line. Kernel SVR is nonlinear, so it might fit a curvy thing. Okay, but SVR is linear, so it fits a line, similar to linear regression, which fits a line. But here, its idea is that, again, I have some margin similar to margin in SVM, but margin of SVM was for classification. Here, margin says I want to have all of the points in my margin. So I fit a line with some margin around it, but the points should be inside the margin. In SVM, we didn't want the points to be in the margin. Here it is the opposite. We want the points to be in the margin. Okay. And the margin, you can see it can be epsilon, the distance. So yi is a label, the target label of data, ith data point, minus this. What is this? This is the equation of the line. So this should be less than or equal to epsilon. Also, line minus yi should be less than or equal to epsilon. These two together means the two margins around the line, right? So label minus line minus label. What do I mean by line? I mean, for example, when x is 1D and label is 1D, okay? Line means that the y of the line it means that predicted label. So this is predicted label. It means y hat. Do you agree? For example, for this point, your actual label might be here. This is y, but you predict it to be here, defined by the line, which is y hat. You want this distance of y and y hat to be smaller than epsilon. Okay? And as you see, its formulation is very similar to SVM. Hence, its name is SVM. Okay, I think, as far as I remember, it's proposed by Tipshirani et al. At Stanford. Okay, as far as I remember. So one class SVM, what does it do? It considers a class of inliers. So what do we do for anomaly detection or outlier sorry, here you can see it as also outlier detection, but let's not talk about that. You have some data points. You can sorry, I think I made a mistake here. This is not for clustering. This is for outlier detection. I apologize. One class SVM is for outlier detection. When I was preparing the slides, I forgot that. So what does it say? Assume what is outlier? When you have a bunch of data points next to each other, they are inliers. When you have some outliers, they are away from the inliers, right? For example, this is outlier, but these are inliers. Do you agree? Do you agree that it can be seen as one class classification? So you can see this one class and the rest as the other class. So it's like a classification problem, but you consider the inliers to be one class and the outliers to be the other class. So this is what the idea behind one class SVM. But they usually use kernel one class SVM. Why? Because it's usually the data is like this. It's usually you need a nonlinear decision boundary, right? If you use one class SVM without kernel, then it means that what does it do? It will assume one class SVM without kernel. It will say that here all of them are inliers and these are outliers using a line. Okay. So what if you have an outlier here? It will say it's inlier, one class. But when you use kernel one class SVM, it can draw this and say this is my boundary for inliers. Okay. SVM in a scalar, we have this, I think. Let me just give me a second. We have this also. Yes. Guys, these are important. So take a look at that. Here, we have linear in scalar, we have linear SVC, we have SVC, and we have support vector. This is a tutorial. So this is a tutorial page or SVM and kernel SVM in scikit-learn, a scalar. Okay, you can take a look at that. For example, here you see when we use linear with linear kernel, SVC with linear kernel. Does it what? By the way, SVC here is SVM. SVM with linear kernel. That's what does it mean? It's equivalent to SVM, linear SVM. That's why the decision boundaries are linear, right? The decision boundaries are linear. Here also, linear SVC is also linear SVM. This is also linear, but with RBF kernel, as you see, the decision boundaries become curvy, non-linear. Here also. Here, for example, it says polynomial kernel is used with degree 3. Here, RBF kernel is used. As you see, when you use different kernels, your results will be different. Okay, and I think you now understand that RBF kernel assumes that the distribution of classes is Gaussian. Okay, Gaussian, because RBF kernel is using Gaussian distribution. And by the way, when you want to do linear SVM, as far as I remember, Sklearn says use linear SVC rather than SVC with linear kernel, because that's much faster. Okay, linear SVC is much faster. I have tried that. It's much faster. And this is a good tutorial. Okay, I think that's good. Now let's go back to our slides. By the way, you can see it has its parameters too. These parameters are all of the parameters that we talked about. For example, gamma. Gamma is the parameter of kernel. We talked about there are some parameters were in the kernel. Do you remember? These are the, for example, it says the kernel coefficient for RBF or polynomial or sigmoid kernel. The degree of polynomial kernel. See, these are the inputs that you can set in the library whenever you want to use this. For example, maximum iterations. What does it mean? Because as I told you, you need to use optimization, iterative optimization to solve SVM and kernel SVM. It said if you pass the maximum number of iterations, stop the optimization. I don't want it to be too time consuming to optimize. Something like that. Okay. Let me go back to slides. Here, acknowledgement and references also for guys. For more information on KKT conditions, dual problem, method of Lagrange multipliers, etc., refer to my optimization techniques course on YouTube. Also, for more information on these, you can take a look at my tutorial paper, KKT conditions, first order and second order optimization and distributed optimization tutorial and survey. For more information on kernels, see our tutorial paper, reproducing kernel Hilbert space, Mercer's theorem, eigenfunctions, Nystrom method, and use of kernels in machine learning tutorial and survey. By the way, the kernels that we talked about, they are also called Mercer kernels. Okay, Mercer was one of the scientists who worked on the kernels. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at University of Waterloo, Department of Statistics. Okay, references. So this is the paper of Rosenblatt, Perceptron, in 1957. Some of them which I remember, I tell you. I don't remember. Oh, this is the Hebbian learning, the paper which proposed Hebbian learning for perceptron. This is Vapnik's paper. I think this is for, yes, 1974. This is for hard margin SVM. The paper proposing hard margin SVM theory of, I think this is a book, Theory of Pattern Recognition in Moscow. Okay. Then Borges, a tutorial on support vector machines for pattern recognition. This is a good one. You can take a look at that. This, the elements of a statistical learning, the famous book in statistical machine learning by Hastie and Tibshirani and Friedman at Stanford. Also statistical learning with a sparsity for sparse machine learning by Tibshirani, Hastie et al. In 2015. This one is the Occam's razor in machine learning and knowledge discovery. This one is locally linear embedding, a tutorial on LLE, our tutorial. Then this one is our tutorial on isomap. Do you remember I told you about isomap a bit? Multidimensional scaling, isomap, and these things. These are nonlinear algorithms. Kernel principal component analysis. This is the paper which proposed kernel PCA in 1997 by Sholkov et al. Who is Sholkov? Who is Sholkov? Remember this. Sholkov is the god of kernels in machine learning. Okay. Most of the kernel papers are proposed by his team. He is in Max Planck Institute in Germany. Okay. Sholkov also in 1998. Nonlinear, these two papers, 10 and 11, are proposing kernel PCA. Unsupervised and supervised PCA, this is our tutorial on PCA. This is the paper for kernel FDA in 1999 by Mika et al. Also Sholkov is here, as you see. This is our tutorial paper on FDA, Fisher discriminant analysis and kernel FDA. This is a training algorithm for optimal margin classifiers, 1992. I think the fifth 15 and 16, these two references are what? Are papers and books proposing kernel SVM. 1992 and 1995 by Vapnik et al. Okay. This you can see Mercer's theorem, feature maps, and smoothing about kernels. This is our tutorial paper on kernels. This one supervised supervised PCA, which we'll see also is kernel supervised PCA, uses representation theory. Okay, that's one thing. Introduction to RBF networks. I told you RBF is also used in RBF networks. Multivariate density estimation. This is a good book for kernel density estimation. Machine learning for quantum mechanics in a nutshell. I think I told you, even if you see nowadays state-of-the-art papers on machine learning for quantum computing or quantum machine learning, they use kernel a lot. Again, this is a book of Hasty and Tipshurani. This is a book of deep learning book of Goodfellow and Bengio et al. So this one, distance measures for PCA-based face recognition. This is a paper which I told you why cosine is good for face recognition. Local features and kernels for classification of texture and object categories. Okay, I don't remember this one. Reducing the dimensionality of data with neural networks in 2006, proposed by Hinton et al. This was what saved neural networks from the winter of neural networks. It said let's initialize neural network with RBM. Hinton also has proposed this a fast learning algorithm for deep leaf networks. This is what ReLU. Yes, ReLU. The paper proposing ReLU by Bengio et al. Bengio's team. This is the paper of Dropout by Hinton et al. Hinton's team. This is a tutorial on support vector regression. This you can take a look at that for SVR, support vector regression. Sholkov and Smola. These are two important scholars. They have talked about it. Sholkov also support vector method for novelty detection. This is one class SVM for outlier detection. Okay, and this is our paper on KKT conditions. Okay, let's have a break and come back at 8:25. But after break, what we are gonna cover the rest of the basic classification algorithms, and we will also hopefully we can cover most of them, almost all of them, and also including 3 KNN, naive Bayes, and many cool algorithms. And later we will cover in the later sessions, we'll cover fitting mixture distributions to data, also point estimation, and then we'll go to dimensionality reduction algorithms. There is a huge family of methods such as PCA, kernel PCA, FDA, kernel FDA, isomap, LLE, random projection, and all TSNE, TSNE, UMAP, and all of these. They are used a lot in machine learning. Okay, see you back at 8:25. Thank you. Okay, so now that we talked about LDA, QDA, we talked about SVM, kernel SVM, some other basic algorithms we are gonna cover. Okay, one of them is K nearest neighbors. Although you might be thinking that K nearest neighbors is too easy for us to listen to. What happened? What happened really? What? Did I do that? I don't know what happened. It was a bug. Okay. So although you might He's saying that it is too easy to listen to. No, it has some insights, and you will see that even in the later slides of this slide deck, it becomes more complicated and interesting. Okay. So first off, let's talk about k-nearest neighbors. Okay. Consider the data set xi, I goes from 1 to n, and each of them is d-dimensional. Okay. Some data points are close to each other, and some are far away from each other. Do you agree? Of course, in the space, there are some of them are close, some of them are far. In the d-dimensional Euclidean space, okay, we can calculate the Euclidean distance between every pair of points in the space. Euclidean distance or any other distance. Usually we use Euclidean distance. We can use Manhattan distance, L1 distance, norm distance, any other distance. It should be a distance metric at least. Okay. Then consider a point xi. We can calculate the Euclidean distance of all points of data set except itself from this point. Do you agree? So this, what is this? The distance of x1 and xi. L2 norm of xi minus x1 minus xi is the distance, Euclidean distance between x1 and xi. This is a Euclidean distance between x2 and xi. This is a Euclidean distance between xn and xi. So you calculate the distances of all points from the xi, except itself, because distance of itself from itself is 0, right? Okay. We sort these distances in ascending order, so from small to large, and keep the k smallest distances. Okay, this is what we do in k-nearest neighbor. So the corresponding k points with the smallest distances from xi are called the k-nearest neighbors of xi, or in short, KNN of xi. Okay, so what do I mean? KNN of xi are the points, the k points, which are closest to xi as neighbors. Note that k is a hyperparameter. It's a positive integer number for the number of neighbors. Do you agree? Okay. We do this procedure for all n points of data set to have KNN for all points. Okay, so we do this. So we did it for xi. Now do it for all of the points. Okay, so for every point you will have k-nearest neighbor. Okay. Then consider a graph. Consider a graph. So what is a graph? Has vertices and edges between the vertices, right? If you have all of the possible edges between every two vertices, then it becomes a fully connected graph. Okay. We have various graphs, various famous graphs in graph theory. One of them is fully connected graph, also called complete graph. One of them is Erdos-Renyi graph. It becomes something like islands, but islands which are almost connected to each other. Erdos, do you know Erdos? He was a great mathematician. I think you have heard of Erdos number. Even he was writing a lot of papers with various scientists around the world, and they compare his works with Euler, and because of many of his collaborators, people said that how much the authorship distance I have from Erdos. If it is 1, is my Erdos number is 1. If it is 2, it's my Erdos number is 2. I think my Erdos number, mine, is 4. Okay, with 4 authors, I reached to Erdos. Okay. So also we have dichastron number. My dichastron number is also 4. So many people who had Erdos number 1 have already passed away. So Erdos was working on graphs a lot, and in collaboration with another scientist named Renyi, they proposed a graph named Erdos-Renyi graph. That's a famous graph in graph theory. So another famous graph is mesh graph, I think mesh grid or mesh graph. And another, so mesh graph is like this. In 1D, it's like this. No, sorry. In 1D, it's like this. In 2D, it's like this. Okay. This is, and also we can have it in 3D and etc. This is mesh, but so this is a bit of graph theory for you to become interested. Okay. If you connect the ends to each other, they become torus graph. I think you can see it in this way and this. Okay. So torus extends mesh with its end. So because I remember when I wrote a paper with Professor Saber Saleh Kaliber, he's now in Europe. We worked on graphs a lot, and it was very exciting to me. So one of them was mesh, one of them is torus, one of them is Erdős-Rényi, one of them was fully connected. So whenever you propose an algorithm which uses some graphs, you should try it on various graphs. Otherwise, your reviewer will say, why didn't you try on this graph? Okay, that's one thing. And many distributed algorithms use graph. So distributed algorithms are closely related to graphs and graph theory. So consider a graph whose vertices are indices of the points 1 to n. Okay, and an edge from vertex j to vertex I exists if xj is one of the k nearest neighbors of xi. So what, guys, please. So we have a point xi. If xj is one of the k nearest neighbors of xi, then we have a vertex, we have an edge connecting vertex j to vertex I, right? By the way, one important thing, is this graph directed or undirected? Let me tell you one example. Consider these 4 points. Do you see these 4 points? Okay. For this, I assume I'm calculating one nearest neighbor. Okay. So k is 1. For this point, assume it's xi. What is its nearest neighbor? This. Right? Do you see that? Now, let xi be this. Guys, are you listening? This is an important example. So once xi is this is its nearest neighbor, one nearest neighbor. Once, consider this bit to be xi. What is its nearest neighbor? It's kind of an outlier, right? But what is its nearest neighbor? This time, this point is its nearest neighbor, right? As you see, this graph is directed. It's not necessarily symmetric. So for this point, its nearest neighbor was this. But for the other point, its nearest neighbor, so this itself is nearest neighbor of the other point, but for it, this is not necessarily nearest neighbor. In other words, let me call this x1. x1, x2, x3, x4. One nearest neighbor of x4 is x3, but one nearest neighbor of x3 is not x4, is x2. So it's not necessarily symmetric. That is an important thing. Okay, therefore it's a directed graph. Okay, such a graph is called k nearest neighbor graph of the data set. Okay, so I talked about k nearest neighbor. Now I define k nearest neighbor graph of data set. So its vertices correspond to the points in the data set. Its edges show whether they are nearest neighbor or not. Consider a matrix A, which is n by n, whose ijth element is this. Aij is 1 if j is one of the k nearest neighbors of xi. Otherwise, it's 0. Is this matrix necessarily symmetric? No. Okay. For the reason I talked about. So Aij is this. It's a bunch of zeros and ones. Ones means that there is an edge in the k nearest neighbor graph. 0 means there is no edge between these two vertices. Okay. This matrix shows the indices of KNN for all points. It is called, what is it called? It's adjacency matrix, or the KNN matrix. So both are, it's called both of them. It's used a lot in machine learning, especially in machine learning, which uses graph. So adjacency matrix or KNN matrix. Also, it's used a lot in dimensional reduction. Usually, the main diagonal of the adjacency matrix is 0, or it is ignored. Why? Because we don't care. We don't want every point to be its own neighbor. Okay. In some algorithms, especially in graph neural networks, intentionally they add edges from every vertex to itself intentionally. But ignoring those concepts, those new things which have come recently in machine learning, we usually ignore the main diagonal of adjacency matrix. Okay, if k is much less than n, does it mean? N is the number of points, k is the number of neighbors. Then what happens? The adjacency matrix will have a lot of zeros, so it is sparse. Otherwise, if k is close to n, it has most of it is 1. This will not be stored. And again, in coding, we can store sparse vectors as only the indices where the matrix is not 0, right? So in coding, we can write it in a compressed format in a storage. Okay, we can have the adjacency matrix between two data sets with size n1 and n2. Okay, therefore, adjacency matrix in this case becomes will have n1 rows and n2 columns. But if you do use adjacency matrix of one data set over itself, it will be a square matrix, right? Note that one may define the adjacency matrix to be A. Another definition of adjacency matrix might be this: n rows and k columns, where every row lists the indices of the KNN of x1, xi. So the ith row has the indices of k nearest neighbors of xi. Then it will be n rows and k columns, right? This is another way to define adjacency matrix. Right? Okay. Now KNN for machine learning. So KNN can be used for machine learning tasks. For regression, KNN itself directly. So KNN can be used in various machine learning algorithms. But let KNN be itself the algorithm. This is what we do. KNN for regression. What does it say? For every input point x, we find the KNN of x among the training. This is important. Among the training points, not the test point. Okay, we have a bunch of training data points. Among the training points, we find the k nearest neighbor of x. Okay, and this x can be either training point or test point. So x, the input x, might be test or training point, but what we found from the neighbors is from the training points. Okay, the average or some statistics of the labels of the KNN is used as the estimated label. So do you agree that when we have training points, each of these training points has some label, target label? And if it is regression, it is continuous label. If it is classification, it is discrete label. So for every point which comes, or every point in this space, I can find its k nearest neighbors from the training data points, and each of them has some label, target label. So in regression, I can simply take the average of the k labels of the k nearest neighbors. And this will be the estimated label for this point. Okay. Or some other statistics. Someone might take median or any other statistics. Okay. Usually average is used. For classification, it's the same, but rather than average or median or some statistics, what do? We take majority vote, because these are discrete. So for example, in k nearest neighbors, assume k is 5, 3 of them is class 1, 1 of them is class 2, 1 of them is class 3. So the estimated label for this point is class 1. You do a majority vote. You can, if it is a tie, you can have tie-breaking rules and these things. Okay. Then, as explained above, KNN for regression or classification does not have any training phase. This is important. Does not have any training phase. This an algorithm without any training phase. Just testing. We use training points in the test phase. Okay? Because you don't need to fit anything. You don't need to optimize anything. So it's fast for training. It doesn't have any training phase. The training phase of KNN in libraries, but when we see, for example, in scikit-learn, it has some fits, dot fit, which means train. What does it do? It only accepts the training data points and stores them to be used later in the test phase. Okay? The KNN classifier partitions the space into classes. Some of the algorithms partition the space, right? You can see all of the classification problems as partitioning this space, but some of them actually explicitly do that. For example, LDA, QDA we talked about. K-nearest neighbors also does that. They partition the space. If you have two classes, it partitions the space into two parts. Okay, but here the decision boundary will not be necessarily in KNN is not linear anymore, because you are using K-nearest neighbors, and if you see it will be broken decision boundary. Its decision boundary is usually nonlinear. So it's a nonlinear algorithm. It's a nonlinear. So when you do KNN regression, it's a nonlinear regression. KNN classification is a nonlinear classification. The smaller the K, the more variance of the decision boundary of the class has. Okay. Usually when you increase K, the decision boundary becomes more smooth. Okay. When you have a small K, it will have a lot of oscillation. So the smaller, the more variance you have. Therefore, the small K leads to overfitting. So you shouldn't have too small K. Usually, for example, K equals 10 is good, usually. So you don't want to have overfitting. In general, larger K in KNN or regressor results in less overfitting and better generalization. But however, there is a trade-off, as always. Larger K has more computation, right? You need to calculate. Therefore, there is a trade-off between generalization and computation. Okay. I know these are too simple, but now it becomes a bit interesting. Kernel KNN. We talked about kernel SVM, kernelization, and this is now let's talk about kernel KNN for machine learning. We can kernelize the KNN algorithm. Let phi be the pooling function from the input space to the feature space, or reproducing kernel Hilbert space. Recall the kernel trick. This was a kernel trick, right? This was called kernel function. The squared, this is an important thing. This reference one is a paper by Sholkov, the god of kernels, published in NeurIPS. The squared Euclidean distance between points of the feature space, in the feature space, is this. So we can calculate the Euclidean distance in the input space. Euclidean distance in the input space. Do you agree? We can calculate. However, now after pulling to the feature space, I want to calculate the distances in the feature space. Okay. Interestingly, we will see now that the distance, Euclidean distance in the feature space, can be written as inner product of pooled data. Therefore, it can be written purely as kernel functions. Okay, interestingly. So this is the Euclidean, do you agree this is the Euclidean distance? This is the distance, the squared distance between phi xy and phi xj, right? We usually don't know phi, but let it be a hypothetical phi, okay? Now, we will see that it will be like this. Here is the proof. So this, recall this formula. This is quadratic, x transpose x. Now I see this transpose this, right? I apply this transpose into the parentheses, so this becomes phi of xi transpose minus phi of xj transpose. And then I multiply the terms by each other. I'll have phi xy transpose phi xi, phi xj transpose phi xj minus phi xi transpose phi xj minus phi xj transpose phi xi. This is inner product a scalar. I can change the order. Therefore, it becomes these two become minus 2 phi xi transpose phi xj. Interestingly, this is kernel of xi. This is kernel of jxj. This is -2 kernel of xi. Very shocking. So we could calculate the distance in the feature space using kernel functions. Okay. Now we are going to use this for KNN. So for calculation of the distances of points, we can pool the points to the feature space and then calculate their distances in that feature space. Note that here, as we see, the distance doesn't care about phi's. It only cares about phi transpose phi, which is a kernel function, right? So we use this distance in KNN formulation, either for regression or classification. It becomes kernel KNN. Kernel KNN. Kernel KNN can be used similar to how we use KNN for classification. Now, a bit more complicated. Okay. Distance metric learning for large margin, nearest neighbor classification. Okay. Let's talk about generalized Mahalanobis distance. As I told you in one of the classes, I don't remember which one. So Mahalanobis was one of the great mathematicians, Indian mathematicians, who lived in England. Another great Indian mathematician was Ramanujan. Ramanujan was in number theory. Mahalanobis was in statistics. They met in England. I think Cambridge. I'm not sure. Okay. You can see, watch the video, The Man Who Knew Infinity, right? About Ramanujan. It shows in that movie that he meets Mahalanobis. Okay. What did Mahalanobis say? So Euclidean distance has a big flaw, and Mahalanobis found that. What is that? Consider these two classes, x1 and x2. These are two classes, and I have a test point x. Okay. So I have two clouds of data as classes, and this x comes. I want to use distance from the means of the classes as the classifier. One of the simplest classifiers in classification in machine learning is you have a clouds of data points as classes. Each of them has some mean. When for any test point, you calculate the distance of that test point from the means of the classes. The closest class is the estimation for that test point. Okay. Now let's use that here. When you do that, this distance is much smaller than this distance. Therefore, you will say Euclidean distance, it will say x belongs to x1. But when we see as a human, our human mind says x should belong to x2. So this is a big flaw of Euclidean distance, which ignores the variance of classes. It ignores that. It only cares about the mean. So Mahalanobis said, let me say xi minus xj transpose sigma inverse xi minus mu, the mu of the class. This. So Euclidean distance says this is a Euclidean distance, right? It has a square root 2. Compare these two. This is Euclidean distance, the below one. The distance of xi from the mean of the classes. Okay, but Mahalanobis added sigma inverse of the class in the middle. Why sigma inverse? Sigma is a covariance matrix. A sigma inverse is a covariance matrix. Why? Because here, this point, for the bigger class with the larger variance, this distance should be scaled to become smaller. Therefore, I use sigma inverse. Okay. This was Mahalanobis distance in the previous century. Then people said, let's generalize that. To have generalized Mahalanobis distance. Well, how? This is generalized Mahalanobis. So the third thing is this, xi minus mu or xi minus mu xj, doesn't matter. Transpose a xi minus mu or xi minus xj. Now, so people said, let's replace sigma inverse with some general a. However, a should satisfy some property. It should be positive semi-definite. Why? Because this is a distance still. And for this to be distance, it needs to satisfy triangle inequality. And also it needs to be convex. For this, A needs to be positive semi-definite matrix. It means that its eigenvalues should be non-negative. And here we will see that this Mahalanobis distance can be written in this way. It can be seen as projection of the point onto some subspace, and then in that subspace I use Euclidean distance. This is the proof. Let's see. I go from end to start. Consider this. This is a squared generalized Mahalanobis distance, right? M rather than A, I have denoted by M. Okay, M here. And as M is positive semi-definite, I can decompose it to LL transpose. Various decompositions I can use. One of them is Cholesky decomposition. Okay, doesn't matter. So LL transpose. And then I bring this L inside this parenthesis and this L transpose inside this parenthesis. I note this transpose here. Therefore, transpose changes the order. Therefore, L transpose comes here. Here also I have L transpose. What is it? You can write it as L transpose xi minus xj squared L2 norm, right? And what does it mean? So Euclidean distance is xi minus xj squared L2 norm. Here we have L transpose xi minus xj squared L2 norm. Compare these two. It simply says project it onto the column space of L. Recall preliminaries. Project both xi and xj onto the column space of L, and then use Euclidean distance. Do you see that? So the only difference is that don't use Euclidean distance in the input space. Project it onto a subspace. And then how do we find this L? We can use optimization for our own task. Someone might say, I want the classes to be separated. Someone might say, I want something else. You make it a formulation of optimization where the optimization variable is L. And you do your own task. Okay? So that was a talk about Mahalanobis distance, which was important. Now, so there were some people who said, in order to improve the KNN classification performance, we should decrease and increase the intra and interclass variances of data. This is the idea of Fisher. So we increase the variances of classes from each other and decrease the intra-class variances. Okay. As can be seen in this figure, one way to achieve this goal is what? Is to pool data points of the same classes toward one another while pushing the points of different classes away. So pull the same points of the same class toward each other and push away the classes from the different classes. So, something like this. So anchor and positive have the same label. So we push the positive points toward anchor, but negative points have very different labels. So we push them away from anchor. Okay. As you see, we have anchor, positive, negative. We call this triplet in machine learning. Okay. It's a triplet of anchor, positive, negative, where anchor and positive have the same label and negative has another label. Let YIL be 1 if the data points XI and XL are from the same class, and 0 if they are not from the same class. Okay. Moreover, let eta ij be 1 if xj is amongst the k nearest neighbors of xi. Okay. So consider k nearest neighbors. If xj is one of the k nearest neighbors of xi, then I define a variable named eta ij, a scalar eta ij. It is 1 if it is one of the neighbors and 0 otherwise. Okay. For tackling the goal of pushing together the points of a class and pulling different classes away, okay, the following cost function can be minimized. This is the cost function which we can use. Again, optimization. What do we do? What do we do? Take a look at it. What is this? This is a Mahalanobis, generalized Mahalanobis distance, which we talked in the previous slide. Okay. Eta ij, I have it here, plus some constant, and then a sigma over ij and L. Why? Why do I have sigma over I, J, and L. So these are, all of them are indices of data points from 1 to n. So I from 1 to n, J from 1 to n, L from 1 to n. Because I have triplets. Anchor positive, negative. I have 3 points. Okay. So I have these and also these. Let's talk about this. What is this? First off, what is this notation that I'm using? This is called maximum of that and 0. So I mean maximum of all of these and 0. This is called standard hinge loss in machine learning. Standard hinge loss. Why do we do that? Because we want to say, I don't care if inside of this becomes negative. I don't want it to be positive. As long as it is positive, let it be a cost. If it becomes 0 or negative, don't ignore it. The first term in this equation 5 pushes the same class points toward each other. Why? So consider the first term, which is this, the first term. This is a generalized Mohallovis distance of xi and xj. I want to minimize that. So I want xi and xj to be close to each other. And why do I only, it is applied only when eta ij is 1. It means that only when xj and xj is one of the k nearest neighbors of xi. So push the k nearest neighbors toward each other. Okay. By the way, eta ij is 1 if xj is one of the k nearest neighbors of xi, also with the same class label. I forgot to say that. So if it is one of the k nearest neighbors of xi with a different class label, eta ij is still 0. Okay. So what do I mean by the first term? I'm minimizing that. I mean that push the nearest neighbor of xi toward that if its label is the same. Okay. Then the second term, which is the whole list, what is that? On the other hand, is a triplet loss. That's actually a loss named triplet loss. Okay. It was proposed, I think, by either Facebook or Google, one of them. So what does it do? It increases and decreases the inter and intra-class variances respectively. It decreases the intra-class variances and increases the inter-class variances to separate the classes. How? I think I have talked about it. Yes. So here, take a look at that. Let us talk about it. Why eta ij is 1 if xj is one of the k nearest neighbor of xi and it has the same label, right? It means that it is one of the positive. So if consider xi to be anchor, if xj is one of the k nearest neighbors of xi with the same label, it is a positive. If it is a positive, then eta ij is 1. 1 minus il, what does it mean? What was yil? Yil is 1 if xi and xl are from the same class. When I use 1 minus yil, what does it mean? I only care about when xi and xl are from different classes. If I use, it means that if it becomes 0, I don't care about that, right? When does it become 0? When yil is 1, right? Let me talk it another way. So 2 cases might happen. Yil is 0 or yil is 1. When is yil is 1? When xi and xl have the same label. When is it 0? When xi and xl have different labels, right? For this 1 minus yil becomes 1. For this 1 minus yil becomes 0. It means that this term becomes 0 when yil is 1. It means that I ignore the second term if xi and xl have the same label. Therefore, I only consider this second term if xi and xl have different labels. It means that xl is a negative point. So basically with this, which I'm circling around, eta ij, I'm saying that xj should be a positive for xi. With this, I'm saying that xl should be a negative for xi. Okay? And then, what is this? This is triplet loss. It says that take a look at this. I'm minimizing it. So I'm minimizing this. It means that push xi and xj toward each other. Push xj is a positive for xi. So it should be close, become close to xi. Push it. It is minimized. Minimize the generalized Mahalanobis distance between xi and xj. Right? What is this? This is the generalized Mahalanobis distance between xi and xl, which is between the distance between anchor and negative, but with a minus behind it. When I have minimization of minus something, it means that I'm maximizing it. It means that maximize the distance between negative and anchor. So basically, it means that push the points with the same class to each other and the points from different classes away from each other. Decrease the intra-class variances and increase the inter-class variances. This is triplet loss. And this is just a margin. It means that do it because of this hinge loss. What does it mean? Do it, keep doing that until the distance between anchor and negative becomes 1 greater than the distance between anchor and positive. Assume this is anchor, xi. This is xj. This is xl. So xj has some distance from xi. xl has some distance from xi. I'm pushing xl away, pulling xj toward xi. As long as this distance becomes 1, this one here, stop. That's enough for me. That's enough. The optimization for that term is enough for me. Because the more you continue, this inside the standard hinge loss becomes negative. So I ignore that. Okay? Now we can restate what we have, this cost function using slack variables inspired by what we had in support vector machines. You remember zetas that we had in SVM? Inspired by that, we can use that to restate equation 5 to equation 6. So here, I'm repeating it here. By the way, I denoted this to be these two. Here, take a look at this. So I'm either denoting it by distance with M or by L2 distance with L here. So they are the same, okay? So here, what do? I'm repeating this term here again. And what do I do here? I say, I add this slack variable as also one of the optimization variable. For all L, I do this. What do I have? This is 1 minus YIL, which I have it here. I'm repeating it here. Also, eta ij is I'm repeating it here. But I'm replacing the triplet loss with eta ijl. But here, I'm saying that this, which was inside the triplet, the standard hinge loss should be greater than or equal to 1 minus eta ijl. Okay? If you take a look at that, you will see what I mean. Take a look at inside the hinge loss. It's 1 plus this. Do you agree that I can restate that? Let me think. 1 minus, yes, xi, yes. So here, 1 minus xi minus xl plus xi minus xj. This is exactly what we had inside the standard hinge loss, right? Here, basically, this is this. If you restate this constraint, you will get this. What does it mean? I want inside the standard hinge loss to be smaller than a positive value, eta ij, and eta ijl needs to be non-negative, right? What does it mean? I want it to become small. The standard hinge loss said I want it to become 0. In this optimization problem, restated, I'm saying that as long as it is less than eta ijl, that's enough. But eta ijl, which is a slack variable, should be small, close to 0. Great? Did you get it? That's why we could restate that in this way. And this optimization problem is a semi-definite programming problem. See my optimization course, SDP problem. It can be solved using any optimization toolbox iteratively, such as interior point method. This was a KNN algorithm, but it tried to increase the margin between classes, right? A modified KNN. And it used triplet loss. By the way, triplet loss proposed by either Facebook or Google. What did I think Google. Triplet loss, which in the same paper it was proposed, which for face nets. So what did they do? They proposed triplet loss after this paper. It means that they were inspired by this paper. Google people were inspired by this paper to propose triplet loss for neural networks. Interestingly, they took this loss function and they used that for neural networks. They named it triplet loss. Okay. Now we should solve this SDP problem using optimization toolboxes, which use optimization algorithms such as interior point method. It is solved iteratively. Usually it is slow to be solved because SDP is usually hard and slow to be solved using optimization toolboxes. Okay. Now it pays off. That's why people don't use it much. Okay. But theoretically, it is sound. So it is not used much in practice, although its theory is solid. This method is called large margin metric learning for nearest neighbor classification, one of the KNN variants. Okay. By the way, I and my co-authors have a paper proposing triplet mining for this algorithm. You can take a look at reference 11. It's called acceleration of large margin metric learning for nearest neighbor classification using triplet mining and a stratified sampling. What do I mean by triplet mining? Because when you can either, do you remember triplets, anchor, positive, negative? You can sample them from dataset randomly, right? Randomly. Simply take a random point from dataset as xi, then see its label. From the same class, randomly take another point as positive. From other classes, randomly take another point as negative, and do it for multiple times. You will generate triplets, right? However, we can do it in a wise way. We can do triplet mining. We can say, let's find the best triplets, or the hardest triplets. We want to take hard on our algorithm. For example, we say, I want what is the hardest case for triplet? If the positive is very far from anchor and the negative is close to anchor. This is very hard for algorithm. Then we take all of the hard triplets to train the algorithm better. Or we can take it easy on the algorithm. What is the easiest case? Positive is close to anchor and negative is away. We can have various variations, right? So this is called triplet mining. And this is used mostly for Siamese networks in neural networks. But we found out, by the way, this triplet idea was used previously in KNN. Let's use the triplet mining for this old algorithm. And this is the paper. References: Sholkov, the god of kernel, in 2001, published a paper in NeurIPS, one of the important conferences in machine learning. The kernel trick for distances. Right? Okay. And this spectral, probabilistic, and deep metric learning. This is my tutorial paper for, you can see about Mahalanobis distance and generalized Mahalanobis distance in this paper. This metric learning is survey. Again, distance metric learning, generalized Mahalanobis distance. Let's find the best L for our own task. You can take a look at it. Metric learning by collapsing classes, proposed by Royce. Sam Royce was one of the important scholars in machine learning. Boyd, convex optimization, its book. And Fisher discriminant analysis. Oh, by the way, Fisher discriminant triplet and contrastive losses for training Siamese networks. This is a paper which proposes the idea of Fisher discriminant analysis for neural networks in terms of triplet loss. Okay. Distance metric learning for large margin nearest neighbor classification. What is this? This is the paper for large margin KNN, which we talked about in 2006. What is this? FaceNet. This is the paper of Google in 2015. FaceNet, a unified embedding for face recognition and clustering. In this paper, they proposed triplet loss for neural networks, inspired by the large margin KNN algorithm. Semi-definite programming. About, if you want to know about SDP, you can take a look at this for optimization. Distance metric learning for large margin nearest neighbor classification in 2009. Again, another follow-up paper for that large margin KNN. This is also our paper, which I said we use triplet mining for this large margin KNN algorithm. Okay. Now, KNN algorithm is over. Let's talk about Bayes and naive Bayes classifiers. So what do we have? According to Bayes' rule, the posterior is this. This is the posterior. What is, so this is Bayes' rule, or we call preliminaries. You can see this as a prior of the Jth class. So assume we have several classes. Cj means the Jth class, okay? Probability of X belonging to Cj. This is prior of this Jth class. What is this? This is the likelihood. This is called likelihood. Means that the likelihood of X, if given that X belongs to the Jth class. This is called posterior. The probability of X belonging to the Cj given X. So given X, what is the probability that X belongs to the Jth class? And this is the probability of X, right? Okay, I can name it. I can name this to be Fjx. Also name this to be, I think this needs to be J, pi J. So prior of the Jth class. And this I can marginalize. So rather than this, I can say probability of X given X belongs to the Ck times probability of X belongs to the Ck. This is called marginalization. Okay. Where C is the number of classes. Okay. Now, posterior, probability of X belongs to the Cj given X. This is likelihood or class conditional. This is also called class conditional, and this is prior. The Bayes classifier, what does it do? The Bayes classifier. It maximizes the posteriors of the classes. So it says this is the posterior. Which class maximizes this posterior? And the optimization variable is the label of the class. Which class? Argmax of this for K. Okay. And this is the estimated class label for X. So this is a test phase for the Bayes classifier. So assume you have the posterior, you see which class maximizes, has larger posterior. That's the estimated class for X. Okay. Now, according to equation 1, which we had here, according to equation 1, and Bayes' rule, we have this. What is this? Probability of X being in Ck given X. We can write that it is proportional to the numerator of the Bayes rule, right? So considering that, ignoring the denominator. Okay. Now, what do I do? Where the denominator of the posterior, which is this, is ignored. Because why can't we ignore that? Because it is not dependent on the classes C1 to CC. It's not dependent on its summation. It's over all of the classes. We don't care which class we are in. So we can ignore the denominator. Right? Now equations 2 and 3. Where were these? I'm repeating them here. Okay. According to equation 3, I mean this. the posterior can be written in terms of likelihood and prior. So this was the posterior, this is likelihood, this is prior, right? Therefore, equation 2 can be restated as this. So I can replace this posterior with this. This is exactly what I have done, right? Now, note that the Bayes classifier does not make any assumption on the posterior. Not any assumption on the posterior, prior, and likelihood. Recall that what? Right, recall that. LDA, QDA made assumption. They made assumption that the classes have Gaussian distribution, right? But this Bayes classifier doesn't make any assumption, so it's better. And also LDA, QDA, they assume they are unimodal Gaussian distribution. Okay, for the likelihood. Therefore, we can say the difference of Bayes and QDA is in assumption of the unimodal Gaussian distribution for the likelihood class conditional, right? Hence, by the way, if the likelihoods are actually unimodal Gaussian, then the Bayes classifier reduces to QDA. The Bayes classifier is will be the same as QDA. If the likelihood is unimodal Gaussian, right? Okay. Likewise, the difference of Bayes and LDA is an assumption of Gaussian distribution for likelihood and equality of covariance matrices of classes, right? Then, therefore, if the likelihoods are already unimodal Gaussian and the covariances of the classes are the same, then Bayes classifier reduces to LDA. Now let's talk about naive Bayes. Okay, naive Bayes. So we talked about Bayes. Naive Bayes is a follow-up algorithm. What does it do? Implementing Bayes classifier is difficult in practice. So we approximate it. It's hard to calculate the posterior. So let's approximate that by naive Bayes. Hence the name naive, because it approximates the Bayes. What does it do? If xj denotes the jth dimension of x, so x is a d-dimensional vector, x1 to xd, xj, let it be the jth dimension of x, then equation 4 is restated to this. So what was equation 4? This was it. Argmax of pi of k, the prior of the case class, times P of x given x belongs to the CK, right? Now, I have this. So now, rather than 1x, I have x1 to xd. It's the elements. Is it still equation 5? Is it still Bayes classifier? Okay. But I'm going to approximate it. Bayes classifier for d-dimensional x, right? The term this is very difficult to compute. Do you agree? What does it mean? If x belongs to the case class, what is the joint probability of all of its features? Joint probability. Hard. Okay. As the features are possibly correlated. But what is by chain rule? By the way, by chain rule in probability, we have this. This joint distribution, you can write it as this. P of x1 given x belongs to the CK times probability of x2 given x1 and x belongs to the CK. Probability of x3 given x1 and x2 and x belongs to the CK, etc. until P of xd given all of the other features and x belongs to the CK. As you see, it's very hard. What does it do? Naive Bayes, what does it do? It relaxes that. It relaxes this possibility and naively assumes that all. Why do we say naively? Because it knows that it's wrong, but it makes this assumption, although it knows that it is wrong. Naively assumes that the features are conditionally independent when they are conditioned on the class. All of these are conditioned on the class, right? Conditioned on the class, it assumes that they are independent. So it approximates this, that every feature only is conditioned on x belongs to the CK. So x1 doesn't depend on x2, etc. All of them are independent. Therefore, I can write it as product of probability of xj given ck. J goes from 1 to d. Obviously, it is wrong because the features are related to it, are correlated. But consider an image of a face. Of course, pixels are correlated. Of course, this pixel is correlated to its neighbor pixel, the colors, the texture, and everything. But if you apply naive based on a face data, face image, it says I assume all of the pixels are uncorrelated, unrelated to each other. That's why it's naive. Therefore, equation 5 becomes this. Equation 5, which we talked about, becomes this. I can write this joint probability as this. And I have pi k here too. Right? Okay, now we have Gaussian naive Bayes too. It is using scikit-learn, sklearn. What is it? In Gaussian naive Bayes, univariate Gaussian distribution is assumed. So naive Bayes doesn't make any assumption on the distribution of the xj given ck. But Gaussian naive Bayes makes an additional assumption. It says that I assume that P of xj given ck has a Gaussian distribution. Okay, for the likelihood of class conditional of every feature. Now the mean and unbiased variance are estimated as this. So this is the mean. What does it mean? This is the mean of the case class. But however, note that we are considering the jth feature, right? So this Gaussian distribution is univariate. It's not multivariate. It's not for a vector. It's for a scalar, right? It's univariate, and its mean also is a scalar, right? So it says that only, what does it mean? Only consider the points in this class K, but only their jth feature. Only their jth feature. And this take the mean. Variance, also calculate the variance only for the points in this case class and only their jth feature, but let it be unbiased. So -1 in the denominator is for being unbiased. That's also a scalar because it's univariate. Okay. Then I told you the prior also. The prior, how do we calculate the prior? Similar to how we did it for LDA and QDA. What did we do? We can estimate it by the cardinality of the class K over all of the points. Nk over N. How many points are in the K class over all of the points? Number of all of the points. According to equations 6 and 7, Gaussian naive Bayes. Gaussian naive Bayes. What was 6 and 7? So this was 7. This was 6 for general naive Bayes, right? Gaussian naive Bayes is equivalent to QDA. Why? Because QDA also assumes that the classes are unimodal Gaussian distribution, right? Where the covariance matrices are diagonal. If the, by the way, note that I told you that Bayes reduces to QDA if the likelihoods are actually Gaussian. However, if the likelihoods are Gaussian and the covariance matrices are diagonal, it means that, what does it mean? The features don't depend on each other. Then Gaussian naive Bayes is equivalent to QDA because QDA in QDA covariance matrices are not necessarily diagonal. If they are diagonal in QDA, it becomes Gaussian naive Bayes. So you can see the relation of algorithms. So that is the off diagonal of covariance matrices are ignored. Therefore, we can say that QDA is more powerful than Gaussian naive Bayes because Gaussian naive Bayes is a simplified version of QDA. Right? Okay. Moreover, it is obvious that Gaussian naive Bayes and QDA are equivalent. for one-dimensional data. If we have only one-dimensional data, for scalar data, they are equivalent. Comparing to LDA, the Gaussian naive Bayes and the Gaussian naive Bayes is equivalent to LDA if the covariance matrices are diagonal. Also, they are all equal. Then, sorry. Okay, so whatever I said, now, if the covariance matrices in LDA are diagonal and they are the main diagonal elements are all equal to each other, then LDA and Gaussian naive Bayes are equivalent. Therefore, LDA and Gaussian naive Bayes have their own assumptions, right? LDA, Gaussian naive Bayes on the off diagonal of covariance matrices, it assumes that they are zero, Gaussian naive Bayes. But LDA makes an assumption on the equality of covariance matrices, because equality of covariance matrices is not an assumption which Gaussian naive Bayes makes. So Gaussian naive Bayes assumes that the off diagonal covariance matrix elements are zero. LDA assumes that they are equal. The covariance matrices are equal. Okay. As Gaussian naive Bayes have some level of optimality, by the way, Bayes, it can be proved that Bayes is the optimal classifier. Okay. Nothing is better than Bayes. Then why don't people use Bayes classifier? No classifier can be better than Bayes. I think it's obvious. Why? Why is Bayes classifier the best classifier in machine learning? What is Bayes classifier doing? Can you tell me, guys? Equation 4 is or equation 2. Take a look at equation 2. What is this? This is Bayes classifier, right? It's maximizing the posterior. Maximizing the posterior. What is the goal of classification? Which class has better, bigger posterior? When you're maximizing the posterior, nothing better than this exists. Okay. Therefore, Bayes classifier is an optimal classifier. Therefore, they call it also Bayes optimal classifier. Okay. But why don't people use that? Because it's hard to compute this posterior. If you know the posterior, use Bayes classifier. This is the best. Okay. That's why we make an assumption and make it naive Bayes and all other things. So what were we saying? Gaussian naive Bayes, as it is naive, it's not optimal, and also it makes an assumption on Gaussian, but it has some level of optimality. It becomes clear why LDA and QDA are such effective classifiers because of these comparisons that we just made. So LDA and QDA have their merits because they're very closely related to Gaussian naive Bayes. Some slides of this slide deck are based on our tutorial paper, Linear and Quadratic Discriminant Analysis Tutorial. Take a look at that. This is a good tutorial. Okay. The references. Kevin Murphy. This is a good book in machine learning. Machine Learning, a Probabilistic Perspective by MIT Press in 2012. Machine Learning, another book by Mitchell, McGraw-Hill Higher Education in 1997. Central Limit Theorem. Yeah, I think, did I talk about anything here? Yeah, I think I missed this slide. It is noteworthy that the Bayes classifier, I already told you, it is an optimal classifier because it can be seen as an, by the way, there are another analysis of why it is a Bayes classifier, because you can see it as an ensemble of hypotheses or models in the hypothesis space. It's related to pack learning. You don't need to know the details of this. I think for you to understand why Bayes classifier is the best classifier is what I told you. It's maximizing the posterior, okay? But you can take a look at this book, chapter 6, page 175 to see why it is best classifier. In simple words, it is optimal because it's optimizing the posterior of the class. In the literature, it is referred to Bayes optimal classifier. In conclusion, the Bayes classifier is optimal. Therefore, if the likelihoods of classes are Gaussian, QDA is an optimal classifier. Do you agree? Because if the likelihoods are Gaussian, then Bayes classifier reduces to QDA. Okay, and if the likelihoods are Gaussian and the covariance matrices are equal, then LDA is an optimal classifier, because Bayes classifier will reduce to LDA. Often, this is an important item. Often, distributions in the natural life are Gaussian. Okay, especially why? Why are they? Have you thought of why? Mathematics. Why do we say that Gaussian distribution is the most common continuous distribution? There's a reason behind that. Because there is some theorem named central limit theorem in statistics. Central limit theorem. People who have learned telecommunications in electrical engineering, they also have heard of this. Okay. What does it say? It says the summation of, take a look at that, summation of independent and identically distributed variables, or IID variables, is Gaussian. And the signal, this is central limit theorem. So central limit theorem says that, assume you have a bunch of IID variables. If you add them, the distribution of this addition becomes Gaussian. This is proved mathematically. This can be proved. Okay? So when you add a bunch of points, these points might be from different distributions. One of them might be, I don't know, a beta distribution, something else. So they might have other distributions, right? Interestingly, if you add them, and if the number of points is huge, you take a limit where n goes to infinity. So the more you add this, the better this approximation. The more you points from various distributions, when you add them, they become Gaussian. Interesting. Okay. And in the nature, signals add to each other. Signals usually add in the real world, add up. Therefore, Gaussian distribution is the most common distribution in the world. Even the filters in our eyes are Gaussian. Okay, that's why LDA and QDA work very well. Because our data sets are usually natural data sets, blood pressure and these things, right? This explains why LDA and QDA are very effective. Okay, so back to the references. Sorry for skipping that slide. I forgot to mention that. I was saying, okay, for central limit theorem, you can take a look at this paper in 2001. And also, this is the optimality of the naive Bayes. Talks about the optimal. As I said, Bayes is optimal. Naive Bayes, as it is naive, it makes assumption. It has some level of optimality. Okay. This is also our tutorial paper on LDA and QDA. Okay. Now, let me briefly talk about tree. Before tree, I wanted to talk about logistic regression. But logistic regression is a bit of explanation, so I will defer it to the next session. But let me talk about tree and random forest. Okay. So, what is it? Tree. By the way, you might also find this a bit boring, but I think it has its merits. Take a listen to it. It's important. Okay. Tree is used for classification and regression. Tree has a lot of uses in various fields of science. It has been used in optimization a lot. Okay. For example, sequential convex programming, if you remember, for non-convex optimization, in my optimization course, I have explained that, uses tree. Okay, tree is used a lot. Tree is used in machine learning too. Tree is used in machine learning too. Now we are going to talk about that. So it is easy to implement. That's an advantage. Easy to implement. It is intuitive and explains how it is worked. So it can be seen as an explainable AI, explainable artificial intelligence. It explains why am I working. I'm splitting the data in this way. It's understandable. Okay. It is common to use in biostatistics and health sciences. They use it a lot, those papers. Assume we have a data set, xi and yi. So xi's are the d-dimensional data points, and yi are scalar labels, right? The labels are either discrete or continuous based on whether we want to do classification or regression. Let xi be this, denoted by this. So the I point, I have xi1 to xid. So xij denotes the jth dimension or feature of xi. Okay. A tree, what does it do? It partitions the space into regions. Okay. So again, a tree is one of the methods which partitions this. Okay. Such as KNN and other algorithms. It partitions this. What does it do? It splits over one of the features at every split. Okay. Note that it splits over one of the features, one of the dimensions at every split. An example of binary tree in 2D is this. Take a look at that. Let's analyze it. Assume we have 2 dimensions. All right. Then xi1 less than or equal to a threshold s1. What does it mean? This is xi1 axis. This is s1. So for s1, if it is less than or equal to, then go to this direction. Okay. Then if xi2 is less than s2, go in this direction. Then it means less than s2. So less than s1 and also less than s2. It is region 1 here. Right? If it is less than s1 here still, but greater than s2, we come here. So we are here and it is region 2. Right? Now consider we are greater than s1. So we are in this direction. And xi1 then is less than or equal to s3, which is here. Note that in our splits, we might split xi over one feature twice, back to back. Doesn't mean we have to alternate between the features. No. So here we say greater than s1. Also, here we say less than s3. We come here. Well, then xi2 less than s4. S4 is here. It means that we are here. Then it becomes R4. If we are here still, we are greater than S4, we are in R5 here. But if we were greater than xi1 was greater than S3, we are here, so it's R3. And here we don't split anymore. So it becomes, all of this becomes R3. This is how a tree is working. And this is a binary tree. Why? Because every time it splits to 2 regions. Binary tree. The initial region is the whole space. So we have considered the whole space of data. If it is d-dimensional data, then the space is d-dimensional. A binary tree splits a region into 2 disjointed subregions whose union is the parent region. So we have a parent region at every level of the tree. It splits to 2 subregions. This is subregion 1. This is subregion 2. If xij is less than or equal to s or greater than s, and it has 2 parameters, j or s. J is which feature we are splitting on, which dimension, and S is the threshold. Okay, and their union becomes the whole parent region. They are disjointed. There is no intersection between them. Okay. Now J goes from 1 to D, right? J is one of them, 1 to D. There are several questions. Over which feature J do we split? Which feature J? That's one question. Another question, what is the value of threshold S? Okay. Another question, for each region, I want to have an estimated label. What label can I estimate for every region? We are going to answer these questions. Okay, so we define something named local cost function. Local cost. We'll have global cost function too. Local cost function is this. What is it? It says that for every split, I'm using this local cost function, hence the name local, because at every split I'm doing that. Okay. Then I'm saying that for all points in region 1, take C1 bar as the estimated label for that region. And what is C bar 1? This is the average of the training labels in that region. The average of yi's if xi belongs to R1. Okay. So in this region R1, we have a bunch of data points, right? They have some labels. Take an average of these labels as C bar 1. Do this for this region 2. Sorry. Do this for region 2 also. It gives you C2 bar. So do it for the labels in the region 2. So C bar, C2 bar. Then it says that for this equation, this optimization, it says that by the way, J and S, these are discrete optimization. This is not continuous. J is an integer from 1 to D, and S is some float threshold, right? Find a J and an S, a combination of J and S, which minimizes this cost function. And what does it do? It says, I want in each region my estimated labels to be as close as possible to the yi's. So it means that I have an average label for every region. I want the labels of my points to be as close as possible to that average. Do you get it? So I have the least amount of error. This is error, right? This is the error. Error between yi and the estimated label. I want this error to be minimized. I square it also to take it to, doesn't matter, but I can square it for each in derivative and these things. And then I do it for both regions. So I can have a for loop over J from 1 to D, and I also can try different S thresholds. By the way, what thresholds can I choose for S? For a feature J, I have n data points, right? N data points, each of which has a feature J, right? It means that I have n values for feature J. It means that I have only n intervals, right? So x1, x2 until xn. Each of them have some J feature. So I have this, all of them, n of them, right? Does it matter if I'm here or here? I choose S either here or here? No, both of them are below this. It means that don't consider all of them. So you have n intervals. You have only n cases for J, for S, and D cases for J. So this is a loop of ODN. Big ODN, right? A nested loop. This is a nested loop. In each nested loop, you calculate equation 5, and you see which J and S you should choose. Did you get it? We use this for growing the tree. For growing the tree, we use this. Therefore, we find the best J and S so that we have the smallest mean squared error of the estimation of the labels in the region. If the depth of the tree is a small, the number of children regions is a small. What do I mean by children regions? Every tree has some children regions, right? At the end, right? We have some root, and at the end we have some children, the terminal nodes. If the depth of the tree is small, we don't have many children. If the depth becomes too large, we have a lot of children, right? And it means that the more depth we have, the more children we have, the more complex the model is, the more overfitted it is. If it is small, it is underfitting. If it is too small, okay? If it is too big, too deep, it's overfitting. Okay? Therefore, the number of children nodes in a tree T, denoted by T, is a good measure of overfitting and complexity. Okay? Then we'll see in the next session, at the start of the next session, how we can regularize it in a way to find the best way to not to have overfitting. So we learned how to grow the tree. At the start of next session, we'll learn how to prune the tree. We prune it. We grow the tree and then we prune it, not to overfit today. Okay, we'll continue in the next session. Thank you.